My name is Kaan. I'm happy to be here. So I joined Oracle around 2020 March. Before that, I completed my PhD at ETH Zurich in Systems Group. So at Oracle, I'm in the HeatWave team, doing multi-query processing. So and today I will talk about HeatWave, both from a warehouse perspective and lakehouse perspective. And since my topic is mainly query processing, I will focus on that. And I want to give you an idea of how do we do query processing optimization, what are our execution strategies to achieve the very good performance that you have been seeing from MySQL HeatWave. So MySQL HeatWave, as you know, is a query accelerator for analytics, right? For analytics queries, it's known that transactional databases are not good because of their row store architecture and optimization for transactions. They are not fast for analytics queries, and this is where HeatWave comes into place. This is the accelerator for your analytics queries, basically. And queries come into HeatWave, and results get back, and everything is processed in a large-scale cluster, which might consist of many nodes. And each of these nodes have lots of memory, 512 gigabytes, for instance, and 32 cores. So we keep all the data in memory. So we are a completely in-memory query acceleration system. So I would like to focus on the question, how do we scale out query processing to hundreds of nodes and thousands of cores efficiently, right? And I will focus on three aspects in particular. The first aspect is our main principle in execution, in query execution, is high-scale, high fan-out data partitioning. And I will talk about that problem. And the second one is I will talk about various query optimizations. How do we do query optimization from a holistic way? And what are the individual details about that? Please feel free to comment. So maybe you have seen these results, right? So HeatWave Lakehouse on 500 terabyte TPCH benchmark, we are much faster than Amazon Redshift, Databricks, Snowflake, Google BigQuery, and our price performance is also much better. So basically, how do we achieve this, right? So let's start from the fundamentals. The OLAP performance fundamentals, for us, it starts with the data storage. How do we store data? We store data in a so-called hybrid columnar format. And what this entails is we partition data, right? We have many partitions. When we load data to HeatWave, we create these partitions. And then each partition has many chunks, so-called chunks. And in these chunks, we have so-called vectors, and each of these vectors stores some part of your columns. So this is the columnar format. And the reason why we call it hybrid is because it's also horizontally partitioned across these chunks. And then each vector has something called a tile, and the query processing operators work in this tile granularity. So they read each tile one by one, right? And then they process and they produce tiles, and then these tiles are turned into chunks, etc. So this is our main storage format when we do query processing. And high fan-out partitioning, as you might guess, is the core aspect of the performance. So for instance, let's look at how we do a distributed relational join, right? So the query is joining line item orders table on L order key, O order key. That is our join predicate. And imagine we have a 3-node cluster. In each node, we have some part of the line item and some part of the orders. And as you can see now, we need to bring some partitions to different nodes, right? So the first thing that we do is something called system partitioning over the network. So we bring the correct partitions to correct nodes. So this is that. And then the second part is we also do a local partition. So we partition even further. Why? The reason is we want to achieve first multi-core parallelism, so each core needs to have enough partitions so that we can parallelize efficiently. And secondly, not even just the number of cores, we also partition further to achieve cache locality, right? So we want the small side of the join to fit the L1 cache even to achieve very good join performance. So let me try to give you an intuition about that. So how much do we need to partition? So our main join algorithm is hash join, right? So we have the order side, which is the smaller side. We build a hash table on that. And then the probe side is the line item side. The hash table will be probed. So during the probe phase, the hash table will be accessed with very heavy random access, right? So we will do lots of random accesses on the hash table. That is why we want the hash table to fit the smallest cache possible, the L1 cache. And in modern systems, L1 cache is around 64 kilobytes. So we want to really partition a lot to achieve this. So let's do a back of the envelope. Let's say orders key column is 8-byte integers, and then we have 768 billion rows in the 5 terabyte cluster, for instance. That means 6.1 terabytes of data that we need to partition. To achieve 64 kilobytes, that means we need to create 96 million partitions. That's a lot of partitions, right? And we have to do next power of 2. So that comes out to 134 million partitions. So creating this many partitions on this much data in a distributed way is not an easy task. And there are some challenges associated with that. So let me try to give you an intuition about that. So the data partitioning problem, right? Where is the bottleneck? So it's actually a very simple algorithm. You scan your relation. For each tuple, you have a key, you hash it, and the hash tells you which partition the key belongs to, and then you write to that partition. The problem is, in case our fan out is large, so the number P has a wide range, then this causes a lot of random access. And the random access in modern CPUs is a problem because of this translation look-aside buffer. So what is a translation look-aside buffer? It's a specialized cache in CPUs for virtual to physical address translation, right? So if a virtual address is not found in the TLB, then a very expensive page walk occurs. And this is even more expensive than a normal cache miss because it might need multiple memory accesses to get that correct virtual address. Typical TLB has around 64 entries. So any partitioning fan out larger than 64 in such an algorithm will cause massive pain. So it will be very slow compared to fan outs that are less than 64. This problem has been researched a lot, and there's extensive benchmarks about this problem. So here, as we see, for instance, in the x-axis, we have the number of partitions. On the y-axis, we have the billion tuples per second, so the partitioning throughput. As we increase the number of partitions, you see that the partitioning throughput goes down quite significantly. So there are, of course, ways to get a better performance or get better behavior for this problem. One is so-called software managed buffers. So this solution relies on the fact that we have some intermediate buffers that we write into first, and once those buffers are full, then we copy to the final destination, right? So since most of the writes happen to the intermediate buffers, we can control the TLB problem to a certain extent. So here we see, for instance, in this benchmark, again, we have the x-axis partitioning fan out, on the y-axis partitioning throughput. With the software managed buffer solution, we can go up to 2K fan out without much throughput loss, right? Other solutions actually go down quite drastically. So again, if you do a back of the envelope, let's say in a modern OS we have 4 kilobyte pages, 64 byte cache lines, 1024 partitions per page. So this is our intermediate buffer space. So if we assume 32 threads do 2K fan out partitioning, that already consumes the 64 TLB entries that we have actually. So that means anything beyond 2K, so think of this 134 million partitions, right? Such a fan out is not reachable with a single round partitioning. And that is where the multi-round partitioning solution comes into the picture. So this software managed buffers are already done within each round, but now we need multiple rounds to achieve this high fan out partition. And to give you an idea about that, I will just show you something high level. So this is a physical plan of our HeatWave query, right? So let's say we have line item here, and then some group by. So this is the join, and then we have another leg. So all these blue nodes that you are seeing are actually partitioning nodes. So these are partitioning rounds. So for instance, on the line item here, before doing the group by, we do 3 rounds of partitioning, right? And then after the group by, we do even 4 rounds of partitioning, etc. So these multiple rounds allow us to reach the high partitioning fan out that we would like to reach before doing a join or a group by to achieve high parallelism and high efficiency. Yeah.
My question is to the previous slide.
Mm-hmm.
So if I understand correctly, the plan is that rather than have random lookups, you do it in batching, so flush and reload is the optimization.
Correct. So there is still random access, but the frequency of random access is reduced by the size of the Okay, so this is the main, one of the main core principles of HeatWave query execution, right? We do lots of partitioning to achieve good performance once we do the joins or group bys or other analytical operations. So let's now talk about other query optimizations that we do. And how do we do query optimization for HeatWave in general? So in HeatWave, when a query first is submitted, it goes through MySQL parser planner. Then, if we see that the query can be uploaded to HeatWave or should be uploaded to HeatWave, it goes to the hypergraph optimizer and HeatWave optimizer. And these two optimizers work in tandem actually. So the hypergraph optimizer produces some subgraphs, it sends it to the HeatWave optimizer. The HeatWave optimizer creates a logical plan and then a physical plan, and then gives feedback to the hypergraph optimizer about the cost of that subgraph, and then the hypergraph optimizer does further iterations on. So the feedback that the HeatWave optimizer gives are, for instance, cardinality stats from previous runs. So we have something called the stats cache, where we store the previous cardinalities from previous queries, and then this we can give feedback to the hypergraph optimizer. Or we also have our physical cost model that we use. Yes?
Are those from actual runs or from estimations?
From actual runs. We also have estimations, but when we have actual runs, we use them. So as I mentioned, we have 2 types of plans in the HeatWave optimizer. One is the logical plan. And the logical plan, how we match the previous runs are actually not on a query granularity, it's operator granularity. So we match each logical operator to previous runs, and if we find an exact match, then we can use that cardinality. So it doesn't have to be, so for instance, the previous runs, it doesn't have to be exactly the same query, right? Even a single node of that query matches, we can use that for another query. And then in the logical plan, we also do some transformations, which I will talk about in detail. For the physical plan, we do other types of physical plan optimization decisions, right? So for instance, we decide on the join pattern, whether we want to do a broadcast join or a partition join. We decide on our partitioning fan out, partitioning rounds. We decide whether we should attach a Bloom filter, which I will talk about later as well. And we look if we have a data placement on the base relations. So when we load data to HeatWave, we have an option to do data placement. We can either use the primary key or some other key that the customer decides. If the join predicates or the group by predicates match this data placement key, we can actually avoid the system partitioning step and do work on them directly. So this just gives you an idea of the optimization step. So let's talk about the logical optimization. One of the logical optimizations that I really like. This is the push-down transformation. So I think it will give you an idea of the types of transformations that we do on the logical level. So consider this query. This query is TPCHQ17. And here, what we do is we first join line item with part, right? So this is the green join that you see here. And then we have a yellow join, which is the line item part on the main query. So this is happening here. And then we have a subquery where a group by happens, a group by on line item. And you see that this group by result, this subquery T1 is joined with part as well. This is this part, this green part. So from a logical standpoint, it doesn't matter actually whether you do this join first or whether you do the it doesn't matter whether you do the group by first or the join first. So you have the option to push down the join below the group by. And depending on how many rows each operator produces, like the cardinality, it might be a good idea to actually do that. So this is what we try to do on the logical level, right? So we look at such equivalences, and then we try to calculate which one is cheaper. And by pushing this join down below the group by, we can save lots of work. So for instance, without the push down, group by has to process 180 billion rows from line item, this table scan. After the push down, after we do the join, the group by needs to process only 180 million, so 1,000x reduction. And this gives us lots of runtime savings. Now, let me talk about a physical optimization, which is the Bloom filter. So the Bloom filter is a very nice data structure, probabilistic data structure. Just to give you a recap, so you have a bunch of bits that are initialized to 0, and then when you insert a key to the Bloom filter, you hash it, and then the hash tells you which bit to set. So here we set 1, and then we do this multiple times. We insert many keys, and then many bits become 1, many bits still remain 0, and then we do a lookup. Right, so we look up, for instance, key 2, we hash it again. If we see in the Bloom filter that bit that hash tells us is set to 1, we for sure know that key has been inserted to the Bloom filter. But due to the hash collisions, it might be that we get a false positive. So the Bloom filter tells us the key is there, but in fact it's not there, right? So this is the probabilistic nature of the data structure. So false positive are possible due to collisions at insert, and false positive rate can be estimated. So to give you an intuition, to keep the false positive rate low, we basically need more bits, like larger Bloom filters, or less inserts. Like the more inserts we have, the larger the Bloom filter has to be practical to use. And this is a data structure that we use a lot for query optimization. Just to give you an idea, again, we see a physical plan here, right? So we join line item with part. And then we have partitioning nodes. Now, during these partitioning operation, we on the part side, we actually build a Bloom filter, right? And then we build this Bloom filter, and then we send it to this node. And this node, while scanning the line item, doing the partitioning, actually checks the Bloom filter whether the key is there. If the key is not there, it just skips it entirely. It doesn't even consider it in this partition. How much savings does that bring us, right? So it depends on multiple factors. One of those factors is the selectivity of this join, because this is the join key that decides on the Bloom filter application. So if this join is a selective join, that's good, because then that means Bloom filter can filter lots of results. So the join rows here is around 20 million rows. It's a good selective join. So the realistic reduction that we can expect here from the Bloom filter is from 3 billion rows to 20 million rows, right? So we save lots of memory. Instead of 48 gigabyte materialization here, we go to just 300 megabytes. Runtime drops from 2.1 seconds to 0.2 seconds. And then runtime of the join drops from 1.1 second to almost 100 milliseconds. So this gives us lots of savings. A couple of observations here. So we have a false positive rate. Of course, more inserts require larger Bloom filter, but there's a trade-off here. If you make the Bloom filter too large, your cache locality will suffer, right? So that's why we try to estimate what is the minimum size that we require to reach a good false positive rate. And expected filtering, it does not only depend on the false positive rate, but also join output cardinality, as I mentioned. So we also need to know about the join selectivity. We use our estimations there or previous runs again to make a good decision. Runtime improvement depends on the filtering rate. We also know Bloom filter lookups might be costly, so we apply the Bloom filter only if we think that the filtering rate is going to give us good savings. Sometimes it's not a clear-cut decision. In those cases, we might decide not to use it. Right? And the join pattern also matters a lot here, and I will also talk about this in my next talk. So the join pattern, if it's a broadcast pattern, that means the build side is broadcast to all the nodes that we have, right? If that is the case, then we do not need to share Bloom filters across nodes, because each node is going to build the same Bloom filter. They have the same data on the build side. That is a good scenario. If we have, however, system partitioning pattern, that means we need to share Bloom filters and do like a global merge, right? So that becomes costly as well. So this is something that we need to consider as well. So TPCH Q21 is a very good example where this brings us lots of savings, because here we build a Bloom filter on the left side and we can push it down to the bottommost operator. And all these operators that you see in this join leg save lots of work, right? There's lots of filtering happening here, and the runtime goes from 13 seconds to 1 second, for instance. Yes. This. Another optimization that we did while implementing these Bloom filters is we implemented this in a blocked way. So the standard vanilla algorithm, what it describes is you have like m bits, right? And then you can set, depending on the hash, you set k bits to 1. So this can happen anywhere, basically. And each insert lookup requires accessing k cache lines. So this is lots of random access. So, and it's hard to parallelize with vectorized instructions because you don't know where your bits start and end, right? But it has the advantages. You get false positive rate that is better. With the blocked approach, we block the entire Bloom filter into like multiple blocks, and within each block we have so-called sectors, etc. So we limit basically which bits need to be set depending on the hash. Right, and then this has the advantage of, first, we need to access almost like a single cache line or a couple of cache lines per lookup. So this is like good from a random access point of view. And we can vectorize this entire thing. So we can use AVX instructions on x86 architectures. The disadvantage is worse false positive rate, but we can adjust for that by making the entire thing a bit larger. So just to show you the results of this approach. So on the x-axis we have the Bloom filter size. On the y-axis we have the time per hash. As we increase the Bloom filter size, if you do not have the blocked approach, you see that the lookup time goes up very high. If we have the blocked approach with the AVX instructions, we get like 3x speed up. So this is giving us a lot of efficiency in terms of how we implement these lookups. And regarding the impact of using Bloom filters on TPCH benchmark here, for instance, TPCH 512 gigabytes, on this graph we have the query runtimes, so 22 queries, and for each query we have 3 runs. The first run is the baseline without Bloom filter, the second run is the vanilla Bloom filter, and the third one is this block optimized Bloom filter. As you see, with the vanilla Bloom filter, we don't get much runtime improvement because the lookups themselves are costly, right? But with the optimized version, we get almost 30% improvement on TPCH geometry. This graph shows you the memory usage. So memory usage is also very important from HeatWave perspective because we're an in-memory system, right? So memory savings become really important. With optimized Bloom filter, we reduce our peak usage by 11 gigabytes. And the peak usage happens at Q18, for instance. Like this is the problematic query. But if you look at other queries like Q9, Q8, Q5, they save lots of intermediate relation usage. By the way, this thing that you are seeing, that is the same for all runs, this is the base table memory. So base tables are always in memory as well. Right, so and that brings me to my summary slide. So what have we talked about? We have talked about data partitioning as a first principle for HeatWave. We have seen how we do optimizations in our algorithms to achieve good partitioning throughput. We talked about query optimization, how we inform the MySQL Hypergraph Optimizer from our HeatWave Optimizer with cardinality, stats cache, or other cost models. We talked about how logical optimizations might save lots of work, push down transformations. And we talked about physical optimizations. I talked about many Bloom filters. We do lots of other optimizations. If you are interested, you can ask me later. So for instance, we decide on the join pattern, partition versus broadcast, group by pattern, whether we do like high NDV group by, low NDV group by, there are many subtleties there. Data placement key plays a big role in query optimization. And we also have something called late decompression. If I find time, I will mention this in my next talk. So yeah, that's it. Thank you very much.